Here we have a pre-calculus problem. Okay, let's go with the question. Prove log a positive log a square positive log a to the third power positive, and it keeps going positive log a to the nth power equals to n times n positive 1 over 2 times log a. Okay, here we have to prove this statement. Okay, now what I'm going to do is I'm going to consider the stuff we have on the left side, and let me show that it is equal to the stuff we have on the right side over here. Okay, now let me write the stuff on the left side of the equation as it is. It is log a positive log a square positive log a to the third power, and it keeps going positive log a to the nth power. Okay, now let me consider the product rule of logarithms. That is, let me add two logarithms at the same base. That is log base a of m positive log base a of n. Okay, here I add two logarithms at the same base a. Whenever I add two or more logarithms at the same base, what I can do is I can take logarithm once with whatever base I have over here, and I have to multiply the arguments m and n. Okay, this is called product rule of logarithm, and this one can be extended even for more than two logarithms. That is, here we have added only two logarithms. Even if I add more than two logarithms, the same rule can be used. And when I consider the stuff we have over here, particularly the stuff we have on the left side of the given statement, so we have addition of logarithms, and the base of the logarithm is not mentioned. For any logarithm, if the base is not mentioned, we can assume the base is 10, because we have to assume it's a common logarithm. So for common logarithm, the base is 10. So for this one, the base is 10, this one base is 10, this one is base is 10, and this one also is base is 10. Okay, we don't have to mention, we can assume the base for each of these logarithms is 10. Okay, so that is we add logarithms with the same base we have over here. So now what we can do is we can use the product rule of logarithms. So this is we have to take logarithm once with whatever base we have, and we have to multiply the arguments over here, here, here. So that is we get a times a to the second power times a to the third power times it keeps going up to a to the nth power. Okay, here we can consider this a as a to the first power, because whenever there is no exponent for any stuff, we can assume there is exponent 1. Okay, so log, okay, here we multiply powers with the same base a. Okay, whenever we multiply two or more powers with the same base, what we can do is we can take the base once, and we have to add the exponents. When I add the exponents, I'm getting 1 positive, 2 positive, 3 positive, and it will keep going up to n. Let me continue log a, and here we have sum of first n natural numbers over here. There is a formula to get sum of first n natural numbers, that is n times n positive 1 over 2. Okay, now let me consider the power rule of logarithm, that is log base a of m to the nth power. Okay, in this logarithm, the argument is a power. Whenever the argument of a logarithm is a power, now we can move the exponent over here in front of the logarithm. So when I do so, I'm getting n times log base a of m. Okay, here the argument is a power, and this is the exponent we have. According to the power rule of logarithm, we can move this exponent in front of the logarithm. Then I'm getting n times n positive 1 over 2 times log a. Okay, here I got the stuff that is exactly we have on the right side of the given equation. Now I have proved the given statement.